Well, good morning, everybody. So it's 11 o'clock here in Newfoundland, and I see people are tuning in on the Top Hat chat, which is fantastic. So, just as a quick reminder, all of the chat in the course lectures for the next few weeks, it seems at least. We'll probably continue doing them like this on YouTube. We won't have YouTube chat, but rather I'll ask you to chat using the Top Hat feature. So if you, well, hopefully everybody's received their invitation to Top Hat. I know I had to resend a few very recently, and there was a couple of students who actually just registered for the course quite recently, and you've now been able to join as well. So hopefully everybody's been able to do that. So yeah, this morning we are going to start talking about computation. Thank you very much for your patience, as I didn't give a lecture on Wednesday, but instead we had that Q&A session with Ms. Hogan about the lab, and I hope that was really helpful to you in terms of thinking about how we're going to get started and the equipment that you need and how we're going to do the first few labs and all that kind of thing. And we will have updates about the lab hopefully on Monday. I mean, we're really getting down to the wire here in terms of computing infrastructure getting set up. As you can imagine, the people who support computing infrastructure in the university in general, but also in engineering in particular, have had a gazillion extra things to do this semester that they weren't expecting to have to do. So it's, their time is very precious. So we are very hopeful to be able to start the labs next week as per the schedule, but we'll have more updates on that on Monday. Okay, so let me start actually by pointing out a couple of things. So one, I'm going to ask you a question in Top Hat, and I am going to see if this maybe pops up the way that I want it to. Yeah, there we go. So that is not full screen. So fantastic. Every week, hopefully, this will get a little bit better, or every lecture, hopefully, this will get a little bit smoother as we try new things out in this setup. So yeah, this is a question related to the material from Lecture 0. And while you're answering this, let me also point out, in Top Hat, there's another question about your availability for extra lab slots. So over the course of January, or as long as we stay under this modified high COVID impact regime, we will probably need to spread students out. So in order to make sure that the labs are as safe as we can make them, we're not going to put 35 people in a room. We're only going to put 20 students plus the instructor, or possibly both of us, and some TAs. So hopefully everyone will have a chance to answer that question. Please do answer it, because we need to know. Now, if you can't change your lab slot, let me give you a few extra seconds on that Top Hat question. Oh, never mind. This mission's closed. You know what? I'll ask it again while I'm still yakking. Oh dear, is that going to make you re-answer it again? Sorry. If you already answered it, you may need to answer it again. Sorry about that. Yeah, so if you can't make an outside lab slot, if you said, no, the slot that I've got is the only slot that I can make, and I can't make it to another slot, doesn't necessarily mean I have no other holes in my timetable, but it might mean that maybe theoretically it's possible for me to do this slot, but I really can't make that work. That's fine. Just let us know. We would like everybody, if possible, to let us know which of those extra slots you can make it to, and hopefully we'll get enough that we don't have to, we'll have enough to accommodate everybody who wants to come, and we have to stay within particular limits as given by environmental health and safety. So let me give you a few more seconds for people to pop their answers in, and apparently if you answered it once, you have to answer it a second time. Sorry about that. Okay. And now time is running out, and let us see what sort of responses we got. And so, yeah, I mean, this is a fairly obvious question, so hopefully that wasn't a big surprise for anybody. But you are responsible as a professional engineer for your work all the time, even when the software you use doesn't necessarily work correctly. So that's one of the reasons why we want to understand something about software and how it works. Okay, so let us now think about, let's see. There we go. So let's think about what computers are. Now, here's an interesting thing. On Monday, I showed a picture to my Term 8 Real-Time Operating Systems course. And I said, here is a picture of a computer and the fundamental building blocks of a computer. And it's the same picture that I showed you in Engineering 1020. Now, in my Term 8 Operating Systems course, we're going to go into a lot more detail about the way that these three fundamental pieces of a computer work together, the CPU, the memory, and the input-output devices. But still, I show the same picture in Engineering 1020 as I do in ECE 8400 and NG 9875. Now, in Engineering 1020, we only go into a certain amount of detail. We look at these three parts of a computer in a quite abstract way. Whereas in the operating systems course, we go into a lot of detail about them. But still, this picture, although it's incomplete, it doesn't have all the details filled in, it is still an accurate picture of what a computer is. So a computer primarily has three components. So there's memory. Memory, also known as random access memory or RAM. It's called random access because we can access any place in memory that we want to at any given time. Historically, for example, there were computers that you had to have sequential access, so you could read information that was located here in memory and then here, but you couldn't access wherever you would like. So, for example, historically, computers used to use tapes to hold information. In fact, yeah, not quite my age, but people just a little bit older than me may have memories of playing video games on Atari systems that actually used consumer cassette tapes. Then again, who am I talking to? You might say, what's a cassette tape? That's fine. But those were sequential access memories, but a random access memory is something that you can grab from anywhere. So we store information in the computer's memory. So we store something over here and something over there and something over there, and then we can go pull that information out of memory. And we store information in bits. Bits are just ones and zeros. So my computer right here, this particular computer has 16 gigabytes, so it can store 16 billion, approximately 16 billion bytes. Each byte is a bit, so that's 64 billion ones and zeros. And out of this enormous quantity of ones and zeros, we can create order and structure and build programs and make the computer do all kinds of cool things, which is like, it's almost like wizardry, right? When I started my engineering degree, I thought that computing kind of was wizardry. Like, I do not understand, well, I do now. I did not understand how it was possible that a collection of zeros and ones could be tamed and turned into like a program that does something meaningful. Well, we're going to teach you the fundamentals of how that works. So we have memory. And we have a CPU, so that's the central processing unit or the processor, and the objective of the processor is to perform computation. And computation is just computing on things with arithmetic expressions like 3 plus 4 equals 7. A CPU is really good at giving you an answer to a question like, what is 3 plus 4? It is also really good at giving you an answer to a question like, is this value the same as this other value? It's very good at doing that kind of thing. It is not good at thinking abstractly, saying, what is the meaning of this poem or something? A CPU is not good at doing that kind of thing, but it's very good at doing very simple arithmetic and logical operations and just doing them really quickly. And the third thing that you find inside of a computer is I/O devices, input-output devices. So a computer will be able to talk to other computers via a network card. It will be able to, or through a wireless network device. It will be able to interact with a user via the screen and via the keyboard and via a trackpad or a mouse or other kinds of devices. It will be able to interact with other computers like, well, your headphones are probably computers these days, and the computer can interact with those via a wireless standard called Bluetooth. So there are lots of different devices that the computer can use to interact with people and other computers and the outside world in general. In the case of this Grove Beginner Kit, which we're going to be using in the lab, you're going to see that this computer has some different kinds of input and output devices. It has input-out devices such as this one. Well, this is a light that can be turned on or off. This is a little screen that can print messages. We have, sorry, this is hard to do from the back end. Here we've got a little buzzer. Oh, look at that. The names of them are printed on the back. Never mind, this isn't hard at all. There's a light sensor right here. There's a sound sensor here. There's a temperature and humidity sensor. These are all input-output devices. Now, the kinds of input-output devices that my laptop is currently plugged into are things like a microphone and a mouse and things like a nice mechanical keyboard with Cherry MX Brown switches, which are very satisfying to type on. So my laptop is connected to input and output devices, and the computer that we're going to use in the lab is connected to input and output devices. They're very different kinds of devices, but overall the structure is the same, whether you're talking about my laptop, or whether I'm talking about this Grove kit, or whether I'm talking about this remote control, or whether I'm talking about my phone. They're all computers that have the same basic structure: memory, CPU, and I/O. And so, yeah, those parts of the computer exist to communicate, or to compute, to remember, and to communicate. Now, I should mention, by the way, in the chat, do feel free to drop in questions at any time. You don't have to wait for the end or anything like that. I'm very happy for these lectures to be as interactive as possible. I mean, especially when we're remote, it makes it a bit more challenging to be really interactive and responsive. I can't look at your faces and see, for example, whether something I said makes sense or not to you. So do feel free to say things in the chat whenever you like. All right, so that's what computers are, but now let's think about what computers do. So in the memory, the computer is going to, as I said, remember things in its memory. It's going to use zeros and ones to store information. When we get to the very end of the course, we'll get into lots of detail about how that actually works. How is it that the computer can store the number 42 using nothing but zeros and ones? It doesn't get numbers digits 1 through 9 to write in. How is it that the computer actually stores a string of characters? Well, using some of the integer representation techniques, but we can have numbers, and those can be integers, or they can be real numbers, and in computing, those are typically stored in a floating point representation, so integers or real numbers. We can have strings of characters, but we can also have instructions for the computer. So in the computer's memory, we store instructions for the computer, and those instructions are things like, take this value and add them together. Store the result here in memory. Now go get this other value out of memory and then compare the two. And if this one is greater than that one, then do this, and this. Otherwise, if it wasn't greater than that, do this. Those are the kinds of instructions that we can store in the computer's memory. So we're going to see numbers, strings, and instructions. And out of those things, we can build kind of any representation we would like. And then, so computers remember things and they follow instructions. And that's the CPU's job. So, CPUs, their job is to follow instructions. And although building CPUs is a very interesting and complex subject, and for those who go on to computer engineering, you'll learn a bit more about how digital logic works in term 3, and you'll learn about microprocessors in term 4, digital systems in term 5, and by the time you get to term 6, you're going to actually be able to construct simple microprocessor or microcontroller. In fact, you'll be able to do a very, very simple one in term 3 even. You'll be able to build some of these things. But in the meantime, the CPU is the thing that, for our purposes, is a little black box. We don't have to know what's inside of it, but through the magic of digital logic, it can follow instructions. We can point it at a place in a computer's memory and say, here are some instructions for you. Now follow them. So, there's a question. What is the difference between a GPU and a CPU? So a CPU is a central processing unit, and it follows instructions of the kind that I just mentioned. So arithmetic instructions, logical instructions, instructions about accessing memory and stuff. A GPU is a graphics processing unit. So that's something that's usually associated with a graphics card. And it also follows instructions, but a different kind of instructions. It tends to follow instructions like take these 4,000 three-dimensional points and then multiply them with something else using like linear algebra or whatever in order to transform an image that looks like this into an image that has this perspective because the player is running around in the game, and so now the perspective of that image should have changed, that kind of thing. So a GPU follows different kinds of instructions. It can do more things at the same time, but the kinds of things it can do is more limited. So we're going to focus more on CPUs than on GPUs, or indeed on TPUs, tensor processing units, which are more used for neural networking, because again, it can do really cool stuff, but it's in some ways much more limited. There's a more limited number of things that it can do. So I almost said, let me ask you a joke. Let me ask you a question that's meant to be a joke. How do you eat an elephant? Go on, somebody wants to say how you eat an elephant. Lots of typing going on. Lots of people are typing. Yeah, cooking is one part. Yeah, in many small parts. Right, there you go. You eat an elephant one bite at a time. Not bite like a computer bite, but ching. So yes, thank you very much. We eat an elephant one bite at a time. And similarly, CPUs follow instructions one step at a time. The complexity of downloading a web page, so downloading a text file from the internet that contains HTML, parsing that, figuring out what all the elements mean, looking at all the other files it says you should include, going off and fetching those, grabbing things like images, parsing those formats, following the image format in order to actually draw the picture that's supposed to be on the screen, and then taking multiple images and text blocks and things and layering them over top of each other for partial transparency, just so that you can see this slide, because this slide is a web page. Boy, that's a whole lot of complexity, and it sounds overwhelming. But if we can break that big, complex, overwhelming problem into smaller elements and solve them one at a time, and take each of those smaller elements and break that down into a series of step-by-step instructions, then we can teach a computer how to do things that seem unbelievably complex. And some of them are complex. But we have to remember, the CPU is not clever. CPUs are really, and computers in general, are kind of dumb, right? All that a CPU knows how to do is follow instructions, and those instructions are very simple. They are not things like, the CPU doesn't know how to do things like download a web page. Instead, the CPU knows how to do things like send these bytes to that device, read these bytes from that device, store things in memory, add values together, check if something is greater than something else. Those are the kinds of instructions the CPU understands how to execute. So computers are kind of dumb, but computers are fast. So CPUs execute very, very simple instructions, but they execute them one step at a time. They follow the sequence of instructions, but they can execute them really quickly. So the computer I could tell my computer that I want it to add a bunch of numbers together, or add two numbers together a bunch of times. And, that's a very simple thing that I want it to do. And it can't do anything very complicated, but it can add those numbers together billions of times per second. And with the combination of different kinds of very simple instructions that I can give the computer, add these numbers, if this is greater than that, then do this stuff, otherwise do this other stuff, or keep adding these things together until they're greater than this other thing. Those very, very simple instructions executed billions of times a second allow us to do some pretty cool stuff. But where do those instructions come from? So all of the cleverness here comes from people. The computer is not clever. You are clever. You are the one who is going to tell the computer what you want it to do. So the whole process of computer programming is kind of just breaking things down into really simple instructions that something even as simple as a computer can understand them. And that's most of what we're doing in computer programming, taking a complex, hard problem and figuring out how to explain it to a computer. So in some ways, it's almost like teaching, right? I'm taking a subject that you're not familiar with and I'm figuring out how to explain it in terms that you are familiar with so that you can learn how to do something new that you didn't know how to do before. Well, it's kind of like that, except in a really extreme, in an extreme way, because we're going from these complex these complex, abstract, theoretical ideas that really clever human brains can figure out and explaining them in the absolute simplest possible instructions. Okay, so the program instructions, well, where do they come from? So first of all, here's, speaking of philosophical questions, what is knowledge? That's an interesting thing to think about, isn't it? So there are two kinds of knowledge that we can talk about that are really useful for thinking about programming. One kind of knowledge is declarative knowledge or propositional knowledge. So have you heard the word proposition before? Is that a word that's familiar to anyone? If so, what is a proposition? A logical proposition. All right, nobody's biting, though I still see lots of things about one bite at a time. So a proposition is a statement that's either true or false. Okay, yeah, sorry. So there's another sense, in more of like a business sense. A proposition would be like, I'm going to propose something for you. A logical proposition is a proposal of something that is either true or false. So I'm going to say, the temperature out today is no, it's not minus anything. It's 5 degrees outside. So that is a logical proposition. Now, if I said it is minus 5 degrees, that would also be a logical proposition. But one of those propositions is true and the other one is false. Now, you can also, in the broader linguistic sense, not talking about logic, but you can also talk about propositions in a sense that people have mentioned in the chat, and the things of, I propose to you, not that it is positive 5 degrees, but I propose to you that we should, go to this event and do a thing or something. That's another kind of proposition. But when we're talking about logical propositions and declarative knowledge, we're talking about statements that are either true or they're false. So here are some examples, and those examples are things like pi is 3.1415926 something, 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 etc. My name is John. It's warm outside. I like engineering. Which of these propositions is not true? All right, we do still seem to have a little bit of a lag. I tweaked the settings to have less latency, but yeah, the warm one. Oh no, someone said the last one, the I like engineering one. That's all right, maybe you'll come around to it. All right, so it's definitely not all that warm outside, at least behind me here in St. John's. I know some folks are still traveling to St. John's, and maybe it's quite warm where you are. But yeah, so we can have propositions and we can know things to be true, or we can know things to be false. But there's also another kind of knowledge, which is not just things you know, but things you know how to do. So this is sometimes called know-how, in that you know how to do this, that, or the other thing. So the reason it's called imperative knowledge is that so I mentioned, I think on Monday, that we're going to talk about imperative programming, where the imperative tense in language is like saying, do something. Listen up. That is an imperative command. I told you to do something. Similarly, we're going to tell the computer to do things, but also we can have imperative knowledge, meaning we know how to do things. We can write instructions for how to do something. I can tell you how to calculate the square root of 24. I can tell you how to change a tire. I can tell you how to bake a cake. And these things, a step-by-step series of instructions that often involve things like making decisions or repetition, such as, here's how you change this tire. Then I've told you how to change one tire. Now do it for this one, and then this one, and then this one, and then this one. Or if I say bake a cake, I might say, okay, then bake at this temperature until golden brown. Well, that means you're going to have to check. Is it golden brown yet? No, not yet. Is it golden brown yet? No. Is it golden brown? Yes, it is golden brown. Okay, so I should stop baking it now. So a step-by-step set of instructions, a procedure for doing something, can also be called an algorithm. So this is a word that you have probably heard before. And so you might think that an algorithm is like a big, scary, complicated, weird word. It doesn't have to be. An algorithm is just a step-by-step procedure with decisions. Anybody recognize this picture? It looks positively scrummy, doesn't it? That's what Dame Mary Berry would say. She's the lady who's second from the left. People are typing. Let's see what the typing says. The Great British Bake Off. Yes, absolutely. Although, so I first saw this show when I was doing my PhD in the UK, and apparently BBC Canada has to call it something else because the phrase bake off is trademarked by somebody else in North America. So yeah, anyway, the Great British Bake Off is a fantastic show. It's also very inspirational. It's like cake week. I like cake. But yeah, so it's a great show. But an algorithm is like a recipe, right? So a recipe will say things like, well, if it's a Mary Berry recipe, it'll be like step 2, make the jam. Oh yeah, thanks Mary Berry for all that detail. But for other people's kinds of recipe, it'll be add this much flour, add this much sugar, add this much salt, etc., stir, mix, etc., bake until golden brown, all those kinds of things. Here's a mathematical algorithm. So what is this algorithm doing? Step 1, let's assume here that y and x are integers. They have to be integers. So what's this algorithm doing? Bunch of people typing. That's good. That's good. Right. So there are a few different answers here, some of which are getting at like very specific points within it. But overall, big picture, what this is doing is testing whether or not something is even. So this is saying that if you can take a value x and divide it by 2 and get a result, which is also an integer, and if you multiply that by 2 and it comes out to the same thing as what you had originally, well, then the number must be even. Because if you took 7 and divided it by 2, then you're going to get 3.5. Then you decide, well, maybe we round it, so maybe we call it 4. 2 times 4 is equal to 8. 8 is not 7. Okay, I guess the thing wasn't even. Now, there are a few different ways that could play out, so don't worry too much about the specifics of the mathematics of this algorithm, but the purpose of showing you this is that just like a recipe for baking, just like a procedure for doing something mechanical, like here's how you rotate your tires, well, for each tire, do this, 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 and this, we have a description of a procedure that involves decisions, and that can be with foodstuffs, that can be with mechanical things, or it can be with more abstract things like numbers. And that is where we're getting into algorithms for computing. So let's see. Shall I ask you? Yeah, let me. No, not just yet. So first of all, let's show you this. So the sum of integers. So if I give you a set of integers, for example, 4, 7, 2, 11, 5, 8, and 1, first of all, what is the sum of that set? What is the sum of that set of integers? So mathematically, we could write it like this, and certainly the consensus view seems to be 38. Let's see, I don't think I actually wrote down the answer here, but I'm going to guess that enough people are saying 38. Yeah, it's probably 38. So yes, if you add up those values, then you get a number. So mathematically, we could write it like this. We could write down, let us find the sum of all the values in S from 1 to n, and that's how we would write that mathematically. How about algorithmically? So if you were to break down what you just did in your head into a set of instructions, into a procedure for finding the sum of a set of integers, not worrying about programming or the syntax of the Python programming language, but if you just wanted to write down on a piece of paper what are the steps in the procedure for finding the sum of any set of integers, not necessarily just this set, but any set S, such that you could explain them to someone else. So you can pretend they're a computer and they're able to do things like add numbers together, and they're able to make decisions such as, is this less than that? If not, keep doing stuff. An exercise that I would like you to do, and this is not an exercise that's going to be submitted, but this is just something that's purely for your own benefit. But I would like you, as an exercise, to do this, to between now and Monday, ideally, write down a set of instructions for how to add all the integers in a set of integers together, and then explain it to someone else. Or even better, write them down, give it to them, and see if they can follow that set of instructions. And so that person could be a friend who is also in the same class. I mean, I guess in Newfoundland at the moment, it's probably somebody in your tight 10. Or if you're interacting with people virtually, whatever, that's fine. You could be somebody over the chat, that's fine. But try to give your written instructions to somebody else and see what happens when they try to follow them. So it could be someone who's in this class, but it could also be somebody like a younger sibling, right? A little brother who is in elementary school or something, who may not know what a set of integers means, but someone who can follow simple instructions that have to do with add this number, check if this is less than that. Stuff like that. So it could be that this is that you explain this to like a younger sibling or somebody like that, which will help us start thinking about how is it that we explain the procedures for doing things to other people. Because it's not so much about whether you're able to do something, but it's about whether you're able to explain how to do something to somebody else. Okay, so software. We've all heard the word software, I imagine. Let me ask you a question that might seem unrelated, but actually isn't. What languages do you speak? And this is a question that you can answer in Top Hat. Sorry, when I say in Top Hat, I mean there should be a Top Hat question that popped up for you, rather than typing it in the chat. I mean, you can type it in the chat too if you want to. That's also fine, but... All right, I'm seeing answers coming in. Seeing lots of English and French, some French and English comma French. Let's see, we've got Bengali, German, mathematical, Spanish, Urdu, HTML, CSS, JavaScript, Yoruba. I'm not familiar with that language. I learn something a little bit every day. Arabic, Tagalog, Japanese, Bangla, Cantonese, Hindi, lots of languages. Igbo. All right, lots and lots of different languages here. So let's close that question and show those responses. There we go. So like I said, English and French kind of dominate here. But yeah, Arabic, Bengali, Tagalog, Hindi, Bengali, Sinhala, some ASL, very cool. And Python. There we go. So we've got some Python. Someone said HTML. Someone said CSS. Yeah, very good. All right. So there are lots of languages in this world, some of which are natural languages and some of which are synthetic languages, and meaning that somebody kind of made them up. There is a reasonable argument as to whether some languages that people speak are natural or synthetic. So what's it called? Esperanto is kind of a synthetic language that people made up to speak, to be a language of conversation, but it didn't like naturally grow out of any particular people group. There's an argument that Korean is partly synthetic in that it was a language that existed, but then there was a king, someone or other, who said, I will make this language a lot more logical, and like threw parts of it away and reworked parts of it. And so it's partly what organically grew up and partly what was synthetically designed, which is kind of interesting. So we've heard the term software. Well, software is instructions for a computer, and they are expressed using some kind of a programming language. So software is it's softer than hardware. Yeah, that's true. There's software. Software is harder than firmware, which is harder than hardware. Well, we'll mostly kind of ignore firmware for the moment because that's kind of like software. It's just harder to change. But software is instructions for a computer expressed using a programming language. Now, that programming language could be something called assembly language, which means, you know, those instructions that I told you about that the CPU can execute, things like add, compare, go over here and run this code, things like that. Well, those are instructions that the computer can execute, and there's language called assembly language that is like literally just those things. Add this register to that register. If that was greater than 0, then jump over to here and start running those instructions, that kind of thing. But there are also programming, but those languages are challenging to use until you understand quite a bit about how computers work in quite a bit more detail than we have so far. But there are also programming languages like Python. So here is what I described earlier. So, and actually I should change that Python example slightly, and later perhaps we can come back to it and we can explain why this is not quite right. But there is the algorithm we talked about earlier for testing if something is even. This is that algorithm expressed in Python. This is that algorithm expressed in another programming language. It's called C++. So C++ is a language that we used to use in Engineering 1020. We don't use it anymore because Python is just a little bit more accessible. You know, in Python, I can write things like 1 plus 2, press enter, and get the value 3. So it's something that's very accessible. We can start with just mathematical expressions that you already know, and that's very nice. Whereas C++, it starts out with more complexity. However, lots of people will go on to use C++, especially if you go into ECE, you'll use C++ in term 3, but it's another programming language. But there are lots of other programming languages in this world. Assembly language, C, C#, Go, Java, MATLAB, Perl, R, Rust, Scala, Spin, and those are just languages that I've used over the last, I don't know, well, actually, I haven't used Perl in quite some time, but those are just languages that I've used. And some of those I use regularly, and some of those I have ever used. But there are lots of programming languages in this world that can be used to express similar ideas. Some are better at certain kinds of things than other, but these are all different ways of describing algorithms to the computer. And so although these different representations, like the Python implementation of this algorithm and the C++ implementation, they look a bit different. Things are a little bit different as to, we don't have the word int in Python. We don't have to have semicolons at the end of statements, stuff like that. But you can see that there's something that's the same about them. The fundamentals of the algorithm are the same. And so this software, which we refer to as code, and code is an uncountable quantity. It's like sand. You wouldn't say a code, or you could refer to some code. You could refer to code. You wouldn't say I have a code, or I have written a code, or I've written 3 codes or something. That would be like 3 sands or 3 waters or something. It's an uncountable quantity. But code is then something that gets translated into machine instructions. So we take something like Python or C++ and we use a program to convert that into instructions that the computer can understand. Those really, really simple things like fetch this value from this location in memory, divide that value by 2, multiply that value by 2, compare this value with that value. If those 2 values are the same, then do this other stuff. Okay, and so what else do I have here that I wanted to make sure I don't forget to say? So in both of these examples, we're going to translate source code in some programming language that is primarily meant for humans. Source code is something that human beings can look at and understand and express their ideas, and that source code gets translated into machine code, and the machine code is the detailed little instructions, and that's the thing the computer cares about. So source code, believe it or not, is for people. So programming languages, in some ways, they're kind of like natural languages. So programming languages are a way of expressing ideas. Natural languages like English, French, Bengali, all of the other languages that we saw on that list, those are also ways of expressing ideas and expressing semantics, which is meaning. But unlike natural languages, programming languages are much more finely constrained. There is much less ambiguity in a programming language. And this is a bit like mathematics. I could say something to you in English that could be interpreted in lots of ways. If I say, that's not half bad, there's multiple ways that you might seek to interpret the phrase, that's not half bad. There are circumstances in which someone might say, no, yeah, that's it. And if you say no, yeah, is that a yes or is that a no? And sometimes it depends on the context. So there are ways in which people can say something in English or in French or in Tagalog or in any of these other natural languages that we're given that can be ambiguous and sometimes deliberately ambiguous. There would be no poetry if it wasn't for ambiguity. The fact that William Shakespeare was able to completely make up new words out of whole cloth, but people still understood what he meant, that came from the messiness of natural language and the words that existed before that he made stuff up out of. The messiness and the ambiguity is where we can get the linguistic form of the creative arts. So that stuff is really important. We don't have that in math. In math, when I write a summation like we had earlier, you know exactly what I mean. And there is precisely one correct interpretation, assuming that I've specified everything correctly. So mathematics does not have that level of ambiguity. It has a lot more precision, which is much more limiting. It's much easier to be wrong in math than it is in English. In English, there are 4 different ways you could say something, and all of them could be sort of right. And in math, there might be a more limited, or there are more ways to say something which just doesn't make sense. But the precision that you get out of mathematics allows you to express some very complex ideas in a very succinct way. And the same is true of programming languages. So when we are writing code, there should be, now some programming languages have some things that you can write down that have undefined semantics, but by and large, we should have programs that have one meaning. There shouldn't be a lot of argument and debate as to, what do you think? What do you think the programmer was really trying to say here? Instead, this is the meaning in that when you run this program, here's what it's going to do. And we should be able to come to those things unambiguously. So programming languages are languages, but they're synthetic languages, and they have more precision than a natural language. Okay. Now it's also important to talk about the words syntax and semantics. So you've probably heard these words before in the context of natural languages, and they are linguistic terms. That's where they come from. And so syntax is the rules of what makes well-formed language. So you can look at a sentence and say, there's the subject, there's the object. That's a verb, that's a noun, that's an adjectival phrase which contains a verb phrase which contains a something or other, right? These are rules that you can look at and say, yes, that is a well-formed sentence. But just because something is well-formed doesn't mean necessarily that it makes any sense. So if I say, 'twas brillig and the slithy toves did gyre and gimble in the wabe, all mimsy were the borogroves and the mome raths out grabe, that you can look at those sentences and tell me what the verb is and what the adjective is, but what does mimsy mean? Right? But again, that's where things like poetry can come from, the fact that it's possible to construct, well, actually, no, sorry. In this case, this aspect of syntax versus semantics is true for both natural languages and programming languages. Now, Lewis Carroll was deliberately playing with languages and using nonsense words, but you can construct a syntactically valid sentence that doesn't seem to mean anything, or at least we can't know what its meaning is. Semantics is the meaning of something. So in this case, so syntax is saying, is it a well-formed sentence? Does it make sense? Is it a well-formed sentence? Does it make sense as a sentence? Does it follow the rules of grammar? Semantics is, now what does this really mean? And so programming languages also have syntax that say things like, when you have an if statement, you must have the word if followed by white space, followed by an expression, followed by a colon, followed by this, right? So we have these rules about the grammar of programming languages, just like we have rules about the grammar of natural languages, but semantics are, what does this all mean? So now we're going to write some software, which is funny because I haven't told you anything about how to write software yet. And yet you already know what you need to know to get started. So you can think about a problem. So when we write software, generally we're going to find a problem. We're going to figure out what the problem means. How do we solve the problem? And then explain to the computer how we solved it. So can we take our solution, our approach to solving the problem, and break it down into steps for the computer? So let's start with really, really simple problems, such as things that we already know. So here's a question. What is 1 plus 2 times 3 minus 4? And that is a mathematical what? That is a mathematical expression. So you can compute an answer, and then you can check your answer with Python. So how in the world are we going to do that? Well, if, for example, and I've linked here to a website called REPL.it, REPL.it. I can, on the right-hand side in this box, we'll ignore the stuff on the left for now, but this box on the right-hand side is an interactive Python shell. I can type 1 plus 2, and then a star, an asterisk, which means times 3 minus 4. And what answer do we get? Well, hopefully we get the same answer. Actually, sorry, I'm not going to click run. I'm just going to press enter here. And it says, well, the answer there is 3. Okay, so very good. Well, what in the world did we just do? Well, we wrote an expression And that expression in Python looks an awful lot like the expression in mathematics, and you all know mathematics. So if you are here, you don't have to know anything about Python yet. I'm going to teach you stuff about Python. I expect that you have at least a few years of mathematics under your belt. Not anything very complex, but you are a bright and intelligent person who has a mathematical education. So you wrote an expression that looks like a mathematical expression, and then that expression was evaluated. So just like in algebra, where an expression is a bunch of values and operators that evaluate to a value, it's also true in programming. In programming, an expression is a bunch of values and operators that evaluate to a value. So when you evaluate an expression, you get a result. And it turns out that in programming, we even use all the same rules that you're familiar with about things like operator precedence. The multiplication happens before the addition and the subtraction, for example. So here is exercise 0. And a few people saw this in Gradescope, and sorry, I had originally meant to introduce this on Wednesday and then have it go live on Gradescope, and then you would submit it today, and a few people noticed, but then I was unwell on Wednesday. I mean, for a good reason. I was getting my booster shot, so hooray. Yeah, unfortunately, whenever I get an immunization, it hits me like a ton of bricks the next day, and then I have an awful day with fever and then I'm all better. So now I'm great. Well, at least I'm feeling better. So I apologize if you saw that in Gradescope and panicked. You were like, oh no, we've got something to do on Friday, and he didn't even tell us what to do. Well, now I'm telling you what to do, and this will be due on Monday because there's not very much to it. So you need to submit a Python expression that evaluates to 42. Now, as an exercise, you can do this by yourself or you can do it together. You can do it with friends. I don't care who you work with on this, as long as you learn something from it. So you are going to submit a Python file to Gradescope, and that Python file should contain an expression. So just to be clear, you should not submit a Python file that contains this, that contains like everything that you would see in a Python shell. It shouldn't even contain this, right? With like lots of stuff that we haven't talked about in the course yet. I just want to see an expression. So submit a Python file that contains like 21 plus 21 or 42 or 1 plus 1 plus 1 plus 1 plus 1 42 times. You can do whatever you would like. This is an opportunity for you to browse the tools page of the course website and figure out what kinds of tools you're going to use. So for example, to write a .py file, you may want to use a text editor. And there are lots of options, many of which are, well, almost all of which are free and many of which are built into your operating system already. But you need to be able to produce a text file that contains an expression which evaluates to 42. And that's it. And you're going to get credit for submitting something that is a valid Python file. This is also an excellent opportunity to figure out which tools are appropriate for the job. So for example, if you write 42 in a Word file and submit the Word file, you're going to see that it doesn't work very well, because a Word file, there's a whole lot more stuff to it than just the expression. So this is an exercise that you can submit between now and Monday. You can chat with me about it. You can do it together with friends. But this is an opportunity to start working with the tools that we're going to need to do a little bit more substantial programming. It can look as simple as this, or even just the number 42. Also, just for fun, there is a leaderboard which does something a little bit backwards. Normally in programming, we like to have the... It's a good thing to have a clear, succinct, short explanation for what your program should do. So we like our code to be simple. In this case, this leaderboard is kind of the opposite. It's almost like a contest to see who can produce. Now, you don't get any credit for this, but just for fun, it's almost like a contest to see who can produce the biggest, most complex expression that evaluates to 42. And the more complex your expression is, the higher this number will be. As I said, normally that's not a good thing. We don't like to write, complicated code when we don't have to, but it is just for fun. Someone says, when I select Gradescope on the course shell, it says I'm unauthorized to join. So if you joined the course quite recently, I may need to just sync the roster again. So I'll do that after this lecture to make sure that everybody's able to access it. And someone said, can I do that with Thani? Yes, absolutely. Thani is one of the tools you could use. So in here, you could type 42 and then hit save and then save it as exercise0.py. And there we go. You'll be just fine. Okay, so that's it for now. Sorry, we're a couple minutes over again. But if there are any questions, I'm happy to stick around for a few minutes and answer those questions. If there are any that I think I might want to do live, I'll do them. Otherwise, I'll just type in the chat. So yeah, I'm not seeing a lot of people typing. So at this point, I will end the online lecture and then I'll stick around for another couple of minutes and answer things in the chat before I have to go and get ready for my next lecture in my other course. So I hope you have a lovely rest of your day. Bye.